Suppose you have 120 chocolates to start with. Your friend challenges you to eat half of the remaining chocolates every minute. Fill in the table. Okay, so I start with 120, and then I eat half of them, so I'm left with 60. Then I eat half, so I'm left with 30. And then half, and then half. Half of 7.5, 3.75. And now I have to again figure out how do I jump to 10. So I started with 120 in minute 1. Or minute 0 I started with. After 1 minute I ate half. So that's like saying I multiplied what I had by a half. And then I took what I had, which was a half of what I started with, and multiplied that by half. And then I took that and I multiplied that by a half. So you can see each minute I'm multiplying it by a half. Another way to think of it, of course, is that I've multiplied by a half 3 times at 3 minutes, which is 120, times a half, times itself 3 times. This would be 120, 1/2 squared, and this is 1/2 to the first, and this is 1/2 to the 0. So the general function, so if I wanted to find this for 10, I could do 120 times 1/2 to the 10. You'd have 0.1171875 pieces left, and to the t in general would be 120 times 1/2 to the t equals the amount that you have. Now some people are like, well, it's dividing by 2, and you'd find that it comes out to be the same. I just wanted to generalize it this way because you'll see it often written as a multiplication problem, not a division problem. So graphing this, start with 120, then 60, then 30, then 15, then 7.5, then 375. You get closer and closer and closer to 0. You never quite touch it. We'll talk about that part in a second. So it's asymptotic to the x-axis. It gets close to it but never touches it. When will you only have 1 chocolate to eat? So again, 1 equals 120, 1/2 to the t. So I can divide both sides by 120. And I get 1/2 to the t on this side is equal to 1 divided by 120, which is about 0.0083 bard. So now I could play around with it, and I could do 0.5 raised to the what equals that. I don't know, to the 6th. So if I raise to the 6th, it's 0.01, 7th, 0.007. So it's again between 6 and 7. But again, I could use logarithms if I so chose, and I would know that the log base 1/2 of 0.0083 bard is equal to t. And using my change of base, log 0.0083 bard over log 1/2 gives me t, which I can type in the calculator. Again, if you're not following the log stuff, it's not critical right now. You would just need to guess and check. So t equals 6.9068900596, etc., seconds. So you quickly get to not even a whole chocolate. Now when will you have none? And this comes to an item called Zeno's paradox, which I'll let you look up the details on. But it basically says that if you're trying to travel from point A to point B and you go halfway each time, well, that's halfway there, and then halfway of that, and then half of that, and then half of that, and then half of that, find that you never actually get there, because you can never get to 0. So when can you get to 0? Well, you can never get to 0 chocolates, because you can always have half of the something you have, no matter how small it is. So here we talked about exponential decay. That's what these functions are called when they're shrinking. You'll notice the number that's being raised to the exponent is less than 1 and greater than 0. And the exponential decay function looks just like this. So if you want to recognize it, it's asymptotic to the x-axis compared to the prior problem where we had a growth problem where it looked like this, and by the way, it continues back asymptotic that way. So we'll start trying to use these exponentials.